Time to do some more problems involving partial fractions. So we get to do a little bit more of our algebra. Woohoo! If it's one thing we want to be good at, we do want to be good at algebra because that's our tool set, right? That's how we build up our knowledge of calculus, is on top of a firm foundation of algebra, geometry, and trigonometry. So it's important that we do our practice. If you're following along with the video, make use of the pause button. See a problem that you like, you should pause. Try it yourself first. And if you ever do need help or you want to compare answers, then unpause and we'll compare. All right, well, let's begin. Our first problem. Find the integral of secant theta d theta. Now you might say a couple things. You might say, whoa, hold on, Steve. That's clearly a trig integral. There's no partial fractions anywhere to be seen. But you may even object even further and say, oh, Steve, you silly. We already know the integral to this. It's one of our basic 10 integrals that we know. Why is this even here? Well, the reason I want to do this one is because the way you usually see how to find the integral to secant is it seems like there's a magic trick that happens. It's like, oh, multiply top and bottom by secant theta plus tangent theta. And you're like, why? Just do it. And look, oh, it works. Ta-da! And so it seems like magic. In particular, it says, oh, somebody knew the answer, and so they're like, I'll show you how to get to the answer. And so it doesn't feel great. It gives you sort of like, do we have to do it that way? Does it have to be the only way we can find the answer is if we know the answer from the start? And I want to demonstrate to you that you can get the answer not by magic, but by following basic principles. It does take a little bit more work, but perhaps it's a little bit more satisfying when we get there in the end. Okay, so how do we get there? Well, I say, all right, we don't know how to integrate secant. One of the nice things that we do is we say, okay, if we have a trig integral we don't know, put it all in terms of sines and cosines. So we say, okay, we'll start there. So our integral of secant is the same as the integral of 1 over cosine. And you say, all right, great. And now we say, hey, there's something nice here. See, this is an integral involving sines and cosines where one of our exponents is odd. We love it when we have an odd exponent for a sine cosine problem because that says, pull out whichever one is odd and put it to the end. So in our case, the cosine has an odd exponent, right? It's cosine to the -1 power. Well, -1 is an odd number. So we say, okay, so by our sort of generic idea that says, if you have an odd power, pull that one out to the end and prepare for substitution. We say, all right, we want to put a cosine theta on the end. So we're going to have something cosine theta d theta. Now at this point you're probably saying, but how? There's not a cosine theta upstairs. The cosine theta is downstairs. How do we pull it out? Well, the answer is, of course, you multiply both top and bottom by cosine. So it's 1 over cosine squared times cosine. Now, keeping with our philosophy about what's happening, is we say, hey, this part, the cosine theta d theta, that's going to become our du. So we need to write this first part in terms of the sine. Okay, well, that's where we use the nice identity. Sine squared plus cosine squared equals 1. So this is the same as 1 over 1 minus sine squared cosine theta d theta. And now we're like, great, we're ready to do some substitution. And what's our substitution? Well, this part really was the hint. It says, what you should be doing is a substitution where the derivative is cosine. So that says our substitution we're going to make is sine theta. So u is sine theta, du is cosine theta, d theta. And now what happens? well, we've transformed our integral. It's no longer a trig integral, it's an algebra integral. And in particular, it becomes the integral of 1 over 1 minus u squared du. And not only is it an algebra integral, it's a nice rational function. Aha! So we can do partial fractions on this. Now, what do we need to do? Well, we need to do partial fractions. So we'll do some work on the side here. All right, so work on our side. 1 over 1 minus u squared. Now, 1 minus u squared, that's the difference of squares. 1 squared minus u squared. So it factors nicely. It's 1 over 1 minus u times 1 plus u. So, according to partial fractions, this will have a very nice form. It'll say, look, you can rewrite this as something, I'll put a constant here, over 1 minus u plus something over 1 plus u. Okay, so clear your denominators. And if we do that, we get what? Well, we get that 1 is equal to a times 1 plus u plus b times 1 minus u. So multiplied everything by the quantity 1 minus u times 1 plus u. And now, well, we have to solve for a and b, which means we have to find some method here. I like to first always say, can I choose some nice numbers? Choose wisely. Well, it looks like there's some really good candidates. For instance, if we choose, say, u equals 1, then that tells us that 1 equals a times 2 plus b times 0. So that says 1 equals 2a, or a equals a half. All right, what about u equals negative 1? Well, similar process. 1 plus negative 1 is 0, so 0a, that's gone. Then 1 minus 1 is 2b. Or is it not 2b? No, it is 2b. All right, great. So b equals a half. Beautiful. Now we know a and b. So we get the following. This is equal to the integral of, well, a is a half, so a half, 1 over 1 minus u, plus b is also a half, 1 over 1 plus u. All right, great. Well, these are integrals we can do. Now, let's talk about them. Well, the half is a constant. The integral of 1 over 1 minus u is natural log. Okay, good. Natural log of 1 minus u. Anything else you want to say about this? I will say that when people do this problem, this one step right here is where you might miss something. So there is actually something else. Because of that minus on the inside, you've got to account for it. So the way we account for it is we divide by minus 1. It's our coefficient. So it's actually minus a half, log 1 minus u. Okay, the second one, plus a half, log of 1 plus u. All right, good. Great, actually. Okay, well, let's see where we go. And, plus c, of course. It's an indefinite integral. You couldn't plus see that coming, right? Okay. Well, we're almost done. And what do? We say, aha, this is, well, we can switch the order. So you can say this is a half log of u is sine theta. So half log 1 plus sine theta minus a half log 1 minus sine theta and plus c. Exactly what we would have expected. And we're done. Except you might be saying, I don't think that's the right answer, Steve. I'm pretty sure I memorized my formulas. We're supposed to get the following. We were told that the integral of secant is log of secant plus tangent. And that does not look very log secant plus tangent like. Okay, all right. Let me try again. Okay, so we're now going to do a little bit of gentle massaging to this expression. What can we do? Well, where do we have space? Well, maybe we'll work down here in the bottom. We'll hopefully have enough space to do it. And the half I can just pull out because half is common. And when I have a log minus a log, well, I can make that subtraction becomes division. So I can say, look, it's really 1/2 log of the top 1 plus sine theta and the bottom 1 minus sine theta. Okay, I'm not going to worry about the plus c. All right. Now, well, this minus downstairs, we're not big fans of that. Let's get rid of it. So how can we get rid of it? Well, you may have noticed I left a suspiciously large gap there. Well, I did it for a reason. We're going to multiply by our conjugate, and 1 plus sine, 1 plus sine. Now, why that? Well, what will happen is the following. You see, if you multiply by the conjugate downstairs, you'll get 1 minus sine squared. And that can be replaced by cosine squared. So you can get rid of stuff. We love it when we get rid of stuff. Makes it feel like we're making progress. Okay, so that's 1/2 log. Now, let's see, what can we say? Well, let's multiply out the upstairs. What do we have? We'd have 1, then plus 2 sine theta, plus sine squared theta, and downstairs 1 minus sine squared becomes cosine squared. All right, cool. Well, what do we have? If we go through now term by term and say let's divide the cosine squared in, what do you see? Well, you'll see secant squared, because if you take 1 over cosine squared, that's secant squared. The very last term is a tangent squared, okay. Now what about the middle term? The middle term you have 1 sine over 2 cosines. So what do we need to do? Well, we need to do something. What we can do is you can say, okay, let's take a sine over a cosine and a 1 over a cosine. And so what we can do is that this sine over cosine squared, you can write it as a secant, that's the 1 over cosine, and a tangent, that's the sine over cosine. And now we say, oh, secant squared plus 2 secant tangent plus tangent squared, well, that is the same as what? Well, as secant plus tangent squared. And now, properties of logs, the 2 can come down. So bring the 2 down, cancels with the half, and we end up with log of secant plus tangent. And therefore, it is the same answer. But we didn't have to go through and say any like, out of nowhere, do this one trick. We were all saying, all the things we did are standard procedures, right? All right, rewrite in terms of sines and cosines, pull out 1 power of cosine, make a substitution, work partial fractions. All these are standard tools in our tool chest, no magic tricks required. Okay, finally, once and for all, we know the integral of secant. Woohoo! Yeah, good. All right, well, let's continue. So our next problem. Find the integral 1 over y squared plus 5y plus 6 quantity squared dy. All right, this definitely feels much more standard in terms of partial fractions. now we just have to decide, okay, what do we do? What do we do? Well, let's talk about y squared plus 5y plus 6. Has that been factored as far as possible? And if not, what do we need to do to it? Well, can it factor further? If it could factor, it would need to have two things that multiply together to give 6 and add together to give 5. I think we have some numbers that do that. 2 and 3, right? So we could say, oh, this is really y plus 2 times y plus 3 on the inside being squared. And so we say, okay, so our real problem is that this is the integral of 1 over y plus 2 squared, y plus 3 squared dy. All right, so that's our integral. Well, partial fractions time. And I think partial fractions is going to be the bulk of the work. And that's not that unusual. In many calculus problems, if you look at the actual amount of time doing the calculus part, it's really usually just a couple of steps. The majority of the work is algebra, which is why we really highly value good algebra. Because when we have good algebra, that helps sets us up for success. And after all, that's what we want. We want to succeed. That's our goal. Okay, so what do we have? Well, partial fractions will say 1 over y plus 2 squared times y plus 3 squared. Well, the denominator dictates the form. I should have paused and said, hey, do we need to do long division? And the answer is no, because the power on top is a 0th degree polynomial. It's 1. So we definitely don't need to do long division. All right, so what do we have? Well, this is going to be the following form. So we see y plus 2, and it's repeated. So what we have to do is we have to have it for every time it's there. So there's going to be a y plus 2 to the first and a y plus 2 to the second. Similar, we're going to have y plus 3 will also be there twice. So y plus 3 and a y plus 3 squared. So we're going to have 4 terms in our partial fractions decomposition. Now, what goes on the top? Well, here it's a y plus 2, so that's going to be a. Now, here it's y plus 2 squared, and so on top we're going to put b. Yeah. Now, this is a part where a lot of people, they get a little bit when it comes to partial fractions. They say, wait a second, isn't it because it's squared? Shouldn't it be like a by plus c? And the answer is, be careful here. You want to not confuse two different things. So when you think of the by plus c rule, that would be if we had an irreducible quadratic downstairs. And this is not an irreducible quadratic, it's just a linear term that happens to be to a higher power. So be careful. Okay, similar, you'll get a c and you'll get a d. So we have to solve for these 4 coefficients. All right, well, standard idea, clear your denominators. So we get the following. 1 is equal to a, and when we clear our denominators, we're going to multiply everything by y plus 2 squared, y plus 3 squared. So we're going to have 1 y plus 2 cancel, so we're still left with a y plus 2 and a y plus 3 squared. On the b term, well, both the y plus 2 cancel, so it's a y plus 3 squared. On the c term, we still have both y plus 2's, but we also have a single y plus 3, because we only had one of them cancel. And on the d term, we only have the y plus 2 squareds. Great, good. Now at this point, you're probably like, we're going to be here a while, aren't we, Steve? Maybe, maybe not. I always like to start by saying, let's choose. And by that, what do we mean by choose? Well, choose nice values. So what are some nice values to pick? Well, I think nice values here, of course, nice values anywhere are ones where things simplify. So that's, when we're talking about making a good choice, we mean make a choice where things get easier. We should always have that in the back of our heads when we're solving a problem. Easier, easier, easier. That's what we want. So here, the kind of thing that would make our life easier is if we did something, for example, chose y to be -2, right? Because that would make any term with a y plus 2 in it go away. Okay, so y equals -2. We'll get 1 equals, and now that term goes away, that term goes away, that term goes away. The only thing that doesn't go away is this term. So that's -2 plus 3, which is 1 squared. So that leaves us with b. All right, we did it. We found b. Woohoo! Yeah, we got it. All right. Well, of course, that's not the only number. We could have also chosen y equals -3, because that's something else where a lot of terms go away. Anything with a y plus 3 goes away. So we're left with 1 equals, and go, -3 plus 2 is -1 squared. Means we're going to get a 1 times d. So, cool. We got b and d. We're halfway done. Ha-ha. We haven't even broken a sweat yet. Well, it still leaves us with a and c. Now, we could, at this point, expand out, or we could say, well, let's just pick a couple more values. Because regardless of which values we pick, it's always going to be true. So let's just pick some values which are relatively easy to work with. How about -1? Keep that pattern going, right? Because I got -2, -3, maybe a -1. We want to pick numbers so that our terms don't get out of control and large. They're easy to work with. So 1. Okay, so let's see what we'd have. -1 plus 2 would be 1. -1 plus 3 would be 2 squared. So that's 4a. Here we'd have -1 plus 3 is 2 squared. So 4b. Here we'd have 1 squared times 2. So 2c. And here we'd have 1 squared times d. So d. Great. All right, so that's what we have. We can also pick another value. Now, we can pick any value. We could pick 0. I'd also say, maybe this isn't the most obvious one to pick. So maybe I should stick with 0. But another thing you could plug in, and you can try it on your own time, is -4. And the reason I point out -4 is -2 and -3 are really good numbers. And you say, well, pick numbers close to -2 and -3. So -1, yeah, also -4. No, why 0? Well, one of the mantras that you can have when you're taking a math course is if an instructor asks, okay, what's the answer? There tends to be one of 3 possibilities. And 0, 1, or it's written somewhere. Okay, usually on the board or the screen, wherever it is you're learning. And so 0 and 1 are really popular choices. So okay, so 0. All right, so if we plug in 0, what happens? Well, okay, so you get 1 equals, and now you're going to get a times 2 times 9, so 18a. And here you're going to get b times 9, all right, 9b. Here you're going to get c times 4 times 3, which is 12c. And here you're going to get d times 4, 4d. Okay, so there's the other one. Now, what we can do is we can update. We know b and d. So we can now take these equations and clean them up. So for instance, this would say 4 times a plus 2 times c, and we have 4b plus d, which should be 5. Bring it over would be -4. here we'd have 18a plus 12c. Now we'd have 9 plus 4 is 13. Bring it over, and we'd end up with minus 12. All right, that's fine. Great. Well, let's clean up a little bit. I can divide everything by 2, for instance. And so 2 times a plus c equals negative 2. And here I can divide everything by 6. That's great. 3 times a plus 2 times c equals negative 2. And now, 2 equations, 2 unknowns, the right number of equations and unknowns. So, what can we do? Well, if you multiply the first equation, say, by negative 2, then you'd have a minus 2c and a plus 2c. Here's a minus 4a and a plus 3a. That's minus a. And here you have a plus 4 and a minus 2. Gives you 2. So that tells us that a is negative 2. Of course, once we know that a is negative 2, we can solve for c. Well, let's see. How could we do it? Well, we'll just plug it into one of our equations. Doesn't matter which one. So minus 4 plus c equals minus 2. So that tells us that c is positive 2. All right, great. Now we have all of our pieces. They're all there, ready for us to work with. So c equals 2, a equals minus 2, and b and d are positive 1. And there we go. All right, great. Well, now what? Well, now what we can do, of course, these are the values. So we'll just make notes here, negative 2 and 1 and positive 2 and 1. All right. So from here, we come back to our integral. We say, hey, we now have a better way to write our integral. See, we're going to pull it apart. So this is going to become the integral of, well, minus 2 over y plus 2 plus 1 over y plus 2 squared. I can write that as y plus 2 to the minus 2, and then plus 2 over y plus 3, and plus y plus 3 to the minus 2. And the reason we're putting things to the minus 2 power is it's setting us up for success by using the product rule, the power rule. So we end up with minus 2 log y plus 2. Okay, that's the integral of the first term. Then here, integral of y plus 2 to the minus 2, add 1 to the power, so it's y plus 2 to the minus 1, divided by that power. So that's minus 1 over y plus 2. Next term, plus 2 log y plus 3. And similar, minus 1 over y plus 3. And of course, plus c, plus c. It's an indefinite integral. Don't forget the plus c. And that's it. We did it. That's not so bad. That's not so bad. You just have to be a little bit patient, keep track of things, and you don't have to go crazy, right? We didn't have to be like, we can only solve for some of our things, so let's just do a lot of work in expanding, because that would take a while to unravel everything. You can always say, let's just choose a couple of nice values to set up a system of equations and unknowns. The key is choose nice values so that the numbers are reasonable. And we want to be reasonable. I like to think mathematicians are reasonable people. All right, well, let's keep going. Okay, our next problem. Find the integral 2x cubed minus 4x squared minus x minus 3 divided by x squared minus 2x minus 3. Okay, this is just another standard bread and butter. Hey, let's do this partial fractions problem. Now, if we look at this problem, what do we see? Well, we go through our process for partial fractions. It says, do we need to do long division? So we check, say, okay, it's degree 3 upstairs, degree 2 downstairs, which means, yeah, we need to do some long division. So we know where we're starting here. All right, so first step, long division. We're taking x squared minus 2x minus 3, dividing that into 2x cubed minus 4x squared minus x minus 3. Now, the process of long division, remember, always says, look at your leading term. The leading term drives what we need to do. So, I have x squared. What do I need to multiply x squared by to get 2x cubed? The answer is by 2x. Okay, so I would have a 2x. Then multiply 2x by the whole thing. And in essence, you're saying, well, because of that 2x, what have I captured? Well, the 2x, because you have that whole process, will capture 2x cubed, which is great. Then you're going to capture minus 4x squared, and then you're going to have plus 6x, or sorry, minus 6x, excuse me. Then we're going to subtract, and then what do we see? Well, the 2x cubed cancels, and here the 4x squared is also canceled, which is pure coincidence. It wouldn't always cancel. What doesn't cancel? What, minus x, and here you have a minus minus 6x, which is 5x minus 3. And now you say, okay, look at the leading terms. Well, in our case, it's x squared and 5x. And you say, whoa, time to stop. Because x squared has higher power than 5x. Once the power here is higher than what you're working with, you're done with long division. And that says you have a remainder. Okay, so our problem really is, after we do our long division, it's the integral, this part, 2x, plus the remainder, the things that's left over here, 5x minus 3, over what we divided by. Now it's time to say, okay, before we write that down, we kind of look ahead and say, we need to do some factoring downstairs, if we can. If not, we need to write it in a better form. Does x squared minus 2x minus 3 factor? And if it does, how does it factor? Well, we need two things that multiply together to give us negative 3, add together to give us negative 2. I think we can come up with numbers that do that. Namely, we have x minus 3 and x plus 1. Right? Because you can check. You get x squared, good. Then you get a plus x minus 3x minus 2x, that's good. And a minus 3 on the end. Good. Okay, so now we're going to do our partial fractions decomposition. So we're going to focus on this last part for a few moments. So we can say, well, 5x minus 3 divided by x minus 3 times x plus 1 looks like something over x minus 3 plus something over x plus 1. Okay, it does bear a resemblance. That's certainly true. Clear your denominators. 5x minus 3 would be a times x plus 1 plus b times x minus 3. And remember, when we say clear the denominators, what we really mean is we're multiplying everything by this common denominator and simplifying. Now we need to choose. Now I should say, there's lots of ways to solve. There's many, many ways. Do it in the way that you're comfortable with. I'm comfortable with making good choices. After all, I became a mathematician, so I know I'm really good at making good choices, right? Okay, so what are some good choices here? Well, good choices are things where you can get zeros involved. So, for example, here I see 3 would be a good choice because that would make that term 0. So by choosing x equals 3, we come to the conclusion 15 minus 3, which is 12, is equal to a times 4 plus b times 0. Well, that says, look, a is 3. Another good choice, if I want to make that term 0, would be negative 1. So x equals minus 1. Minus 5 minus 3 is minus 8. 0a, and here it would be b times minus 4. Well, that tells us, look, b should be 2. And now we're like, woohoo, nice, good numbers. They won't always be good numbers, but if the people who write these problems care for you, they'll be good numbers. And I think the people that wrote these ones cared for us. So it looks like this will be 3, and this will be a 2. All right, well, great. Now, what's left? Well, we still have some work to do, because what we've done is we've identified how to pull that apart. So, updating. We now can say, look, this integral has become the integral. There's still the 2x in front, and now 3 over x minus 3 and 2 over x plus 1. And each one of those is easy enough to work with. The integral of 2x is x squared. 3 over x minus 3, well, that would be 3 log of x minus 3. 2 over x plus 1 is 2 log x plus 1. And as always, don't forget, indefinite integral plus c. And we're done. We're done. So once you get the hang of the process, problems like this aren't so bad. Of course, it always gets more complicated the more interesting your denominator is. But the process itself is not so bad. All right, check. Do I need to do long division? Factor your denominator. Do the partial fractions. Pull it apart by making good choices. And rewrite your integral into nice, easy to handle pieces. Life is good. Life is good. Well, let's keep going. All right, here we go. Ooh, a definite integral. This will definitely be an integral. Well, okay, so what do we have? Find the integral from negative 1 to positive 1 of 3x to the fourth minus 11x squared over x squared minus 4. Okay, no real mysteries here. We see it's very similar to the last one. The only thing that's happened is we've added some bounds, and of course the function is also slightly different, but the process remains the same. We start by saying, okay, do we need to do long division? And we can see the answer is yes, because the power on top is a fourth compared to the power on the bottom. So we would write x squared minus 4. Now, when you're going to do long division, you should always, in the part you're dividing, put little placeholders. It's just a good habit. You may or may not need them, but you never know. So, we only see an x to the fourth and an x squared term, but we should put an x cubed, an x constant term, just in case we need them. And now we proceed by saying, okay, look at the leading terms. The leading terms dictate the procedure. Here, there's an x squared in front. What do we multiply x squared by to get 3x to the fourth? Well, we multiply it by 3x squared. So that's the choice here. So we're going to take 3x squared times the whole thing. That'll be 3x to the fourth minus 4x squared. Minus 12x squared. That's the number 12. I can do multiplication. Yeah, 3 times negative 4 is minus 12. Subtract. 3x to the fourth cancel. There's no x cubed. Minus 11x squared minus 12x squared will leave us with x squared. Okay, what do we multiply x squared by to get x squared? I know that. 1. Okay, so plus 1. Now what? Well, multiply 1 by x squared minus 4. X squared minus 4. Subtract. The x squareds cancel. Minus 4 is 4. And now, look at the leading terms. Wait, x squared has higher degree than 4. So, stop. Long division is now complete. We can update our integral. So what we really have is that this integral is the same as the integral from -1 to +1 of this 3x squared plus 1, and then plus our remainder 4 over x squared minus 4. Okay, there we go. That's our first step, long division. Now we say, okay, we've got to work on that 4 over x squared minus 4. Now we should have right away, and that was really a little clumsiness on my part, said, look, this x squared minus 4, that factors. In fact, it's one of those things that, like, oh, we recognize it almost instantly. Because we see what? We see in x squared minus 4. Well, that's x squared and 2 squared. It's a difference of squares. So it factors a squared minus b squared, a minus b, a plus b. All right, good. So now we go to the side, and we're going to do some partial fractions. All right, so 4 over x minus 2, x plus 2, well, that's going to be something over x minus 2 plus something over x plus 2. Okay, and we can see the form. The form is dictated by the denominator, not by the numerator. Clear your denominators, and of course that means to multiply by x minus 2 times x plus 2. And when we do that, we'll get that 4 is equal to a times x plus 2, and then plus b times x minus 2. And at this point, we need to choose. But we need to choose wisely. Whereas a good choice brings us closer to the answer, a bad choice, it makes it a little bit longer to get there. So again, we look for things that make things 0, and we can see -2 and +2 are great choices. So let's suppose we start with 2. If we plug in x equals 2, we'll get 4 equals a times 4 and b times 0. Okay, so that says a needs to be 1. If we plug in -2, we get 4. Here, a times 0. And here we'll have b times minus 4. So b times -4. Okay, so b is -1. Okay, good. So we say, aha, beautiful. So this is 1, and this is -1. So again, updating our integral. And remember, we haven't done any calculus yet. No calculus has yet been harmed in the solving of this problem. Of course, we would never harm it. We love it too much. We want to treat calculus gently, with love and compassion, because we know if we take care of calculus, calculus will take care of us. All right, so now we've done our partial fractions. We've pulled it apart in a very, very nice way. We're ready. We're ready to begin. And what can we do? Well, we now integrate, right? So here's the calculus part. X cubed plus x plus natural log of x minus 2 minus natural log x plus 2. And evaluate -1 to +1. Now, what happens? Well, when you plug in 1, we're going to get 1 plus 1. Okay, so that's 2. 1 minus 2 is -1. We're taking the absolute value, so it's really log of 1, which is 0. So then minus log of 3. And from that, we're going to subtract what happens when we plug in -1. Well, we'll get -1 minus 1, so that's -2. Log of absolute value of -3. Okay, that's log 3. And here it'd be log 1. Well, that's 0 again. And you say, oh, look, we can combine. And so 2 minus minus 2 is really 4. Minus log 3 minus another log 3 is minus 2 log 3. And we're done. That's it. That's our answer. Now, on a side note, if we had been a little bit more savvy, we could have done one small thing at the beginning. We didn't need to, but we could have, which is the following. This is an even function, which means the function we have at the beginning, if you come all the way back here, if you plugged in positive x or negative x, it's still the same thing. So we could have said, look, instead of going from negative 1 to 1 of this expression, 3x to the fourth minus 11x squared divided by x squared minus 4, we could have said, you know, because it's the same for both positive and negative, I can just go from 0 to 1 and double the answer. And we could have done that. In retrospect, it doesn't make too much difference, except at the end, we'd get to use zeros in our evaluation. And that's always a good time. We always enjoy a nice 0 when we're doing our evaluation. And as a reminder, why is that true? Well, even functions say it has shape like this, so that if we're going from minus a to plus a, the area over here matches the area over there. These are equal areas, so that's why that's true. Okay, good, nice, woohoo! It's fun when we get answers, right? It's a lot better than when we don't get answers. We strongly prefer answers. We're in the pro-answer category of mathematicians. So let's look at another problem. Find the integral of arctangent of cubed root of x dx. Well, okay, what are we doing here? Let's think about what's happening here. And this is not too bad. I think we can make progress here. And what do we need? Well, the arctangent is something we could probably figure out the integral for, but it's not one of the ones we memorize. And then we have that cubed root of x on the inside, which makes us, it really feels weird when we see that. So let's start by doing a little bit to clean it up. So let's make the inside nicer. I don't want to have something that looks like cubed root of x. I just want to have a variable name. So let's make a quick substitution so we can clean up our inside. So let's say we call the inside y. And you might say, well, why not? Well, I just need any symbol. Y is perfectly fine. Pick whichever symbol you're comfortable with. So let's suppose we make the inside a new variable name, so we'll call that x to the 1/3. So that we have, hey, now it's something that looks a little bit nicer. This is just arctangent of y. Okay, that's all well and good, but you've got to follow through and say, okay, you also have to handle this dx thing that's on the end of your integral. What are you doing about that? Great question. Okay, so let's think about that. All right. Well, if y equals x to 1/3, okay, this is fun. Maybe you don't do substitution this way, but bear with me. If y equals x to 1/3, what is x? X is y cubed, right? Okay, I think we're all, yeah, okay, Steve, all right, you speak the true truth. What's dx? So dx would be 3y squared dy. So we say, okay, so our integral, we replace dx by 3y squared dy. Now, you may not be comfortable with doing that kind of idea. I want to point out there are other ways you can figure this out. And here's the way that you often see it done. And so that's an alternative. And just to say, oh, I could say dy, well, that's 1/3 x to minus 2/3 dx. Or, well, since there's no x to minus 2/3, dx is 3 x to the 2/3 dy. But then I say, oh, wait, x to 1/3 is y, so x to 2/3 is y squared. So that would become 3y squared dy. That's another way you could have done it. Whichever way you're comfortable is fine. We're not here to advocate and say, you must do calculus in this particular way. If anything, calculus is that fun part when we start to sort of open up and say, you know, there's sort of a couple of different ways to think about things. And in some problems, you can do things in very, very different ways, using completely different methods, but you still come up with the same answer. And so it's nice to know the wide variety of options available and to be able to use them all. Okay, back to our regularly scheduled problem. We have arctangent of y times 3y squared dy. What do we do? Well, we don't know how to integrate a piece of it. There's the arctangent of y. But we do know how to integrate part of it. We do know how to integrate the 3y squared. So we can do a part of an integration, or perhaps we can do an integration of parts. Integration by parts. Yes, okay, great. So this is a wonderful thing whenever you have something like, there's this little uncomfortable piece. There's this arctangent of y, but this other piece I'm pretty happy with. So we'll say this part, well, that's the part we don't know how to integrate out the top of our head. We'll call that our u term. Everything else, that's our dv. So what do we have? Well, the derivative of arctangent, we know that. 1 over 1 plus y squared dy. And of course, the integral of 3y squared, we know that, is y cubed. Wonderful. Okay, so what do we have? Back to our problem. So we're going to have uv. So y cubed arctangent of y minus the integral v du. The integral y cubed over 1 plus y squared dy. And now we say, okay, here's why we're doing this today. Because it is a rational function. It's a polynomial over a polynomial. So we need to do our traditional how do we deal with rational functions idea. So we see, okay, well, it's degree 2 downstairs, there's degree 3 upstairs, so our first thing is long division. All right, so we're going to take 1 plus y squared. Well, let's put it highest power first. Y squared plus 1. Divide that into y cubed plus 0y squared plus 0y plus 0. All right, and always work with the highest power. Well, I have here y squared to get to y cubed, multiply by y. Okay, so that would leave us with y cubed plus y, subtract, and we're left with minus y. And we say, okay, highest power, y squared minus y. Oh, stop. No more. Because we say, hey, hold on a second. That's a higher power, so we can't do any more long division. Okay, so now updating our integral. So we have y cubed arctangent of y minus the integral of y, then minus, we're going to have y over y squared plus 1 dy. All right, now, what do we do to this, y squared plus 1, or y over y squared plus 1? What do we do if we do partial fractions? Well, the answer is if we do partial fractions to y over y squared plus 1, we'll end up with y over y squared plus 1. You see, y squared plus 1, it's one of those irreducible quadratic, which means we can't go any further. We've gone our limit. And so that's it. We're done. There's no more partial fractions. So So really the only thing we needed was long division. That's okay. Sometimes that happens. No worries. No worries. All right. Well, now we just need to integrate. Okay, so we still have our y cubed arctangent of y. No worries there. The integral of y, 1/2 y squared. Minus minus makes plus. Now, what do you get when you integrate y over y squared plus 1? It's not arctangent, but one thing you could do is you could do the following, is you can make a 2 here, and then put a half in the front. See, 2 times a half, well, that's the same as multiplying by 1. So certainly it's legal. Is it helpful? Well, notice the derivative of y squared plus 1 is 2y. So 2y over y squared plus 1, we see that quite a lot. But in general, the idea of if you see function downstairs, derivative upstairs, the answer when you take the antiderivative is the log of the downstairs. Because that, when you think about going the opposite direction, right? Log of a function, 1 over the function times the root of the function. So what we'll have is the half log y squared plus 1. And of course plus c. Now, are we done? Not yet, not yet. The problem is our answer is in terms of y. We need to go back in terms of x. But we're almost done because we know, for example, y is x to 1/3, and let me say that as x equals y cubed. So we can say, oh, okay, so this is x arctangent of cubed root of x. Okay, then we have minus 1/2. Well, it's cubed root of x squared. We can write that as x to the 2/3 plus 1/2 log of x to the 2/3 plus 1. And plus c. And now we are done. We're finished. Nice, good. You oftentimes will see this kind of idea whenever you see a function of something like a square root or a cubed root or whenever you have like some strange thing going on there. You say, oh, okay, look, really, make a substitution, and then you've transformed it into a parse problem, and then maybe, depending upon where the problem goes, you might have all sorts of interesting things showing up. And we like it when we have interesting things showing up. It makes things more interesting. All right, keep going, right? Okay, so our next problem. A nice little fun problem, which hopefully should only take a little bit of time. Find the length of the curve y equals e to the x for natural log of root 3 less than or equal to x less than or equal to natural log of square root of 99. These are really bizarre numbers. Now, oftentimes the reason they choose bizarre numbers is because something very interesting is going to happen in the process. And so it's sort of a suggestive that, oh, by the time you reach some interesting step, you'll appreciate the bizarreness of these numbers. Okay, I hope so. Well, let's see where we go. I think this one is definitely going to be So we have length, and that's actually pretty straightforward, length of a curve. The formula for length of a curve is the following. Length is adding up a to b, the root of 1 plus the derivative squared dx. Okay, it's just our generic formula. So for us, we have, okay, this is integral log root 3 to log of root 99 square root of 1 plus, okay, now the derivative of e to the x is e to the x. It's a nice function. So if we're talking about the derivative squared, derivative of e to the x squared would be e to the x squared, which is e to the 2x. All right. Now, at this point, I think it's safe to say this does not look like a partial fractions problem. Well, we're still early in the process. Let's be patient. Hopefully partial fraction shows up. If anything, it feels more close to a trig substitution problem. We could kind of go that way, but let's hold off before we do that. Let's not try to get too far into that process. Let's look for a substitution we can make. And let's be aggressive. Let's be really, really, really aggressive. I mean, the most aggressive we could possibly be. And I know you're thinking, well, when he said make a substitution, e to the x, right? And then he said, he wants to be aggressive, e to the 2x. And really? 1 plus e to the 2x? No. We're going to go all the way. Like what? How? Well, by doing the following. Let's let u be that. So we're going to make a substitution, let u be this whole thing. Okay. U equals the square root of 1 plus e to 2x. I almost wrote down dx, but that doesn't come yet. Not yet. Now, can you do that substitution? Yeah, you can. You got to remember, you have to handle the dx. We'll get there. But yeah, we're definitely allowed. We're definitely allowed. Okay, so we have that going for us. Well, what's going to happen? Let's think about the dx. We do have to figure that out. Now, before we do the dx, we are allowed to rewrite things. So, for instance, if I square both sides, that's the same as saying u squared is equal to 1 plus e to the 2x. And that might be a little bit easier to work with in terms of finding the dx. So 2u du is equal to, over here, 2e to the 2x dx. I just take the derivative of both sides. Now we have some good news. The 2 cancels. Like I said, good news. What have we done? Well, not yet. We have to figure out how do we handle this e to the 2x dx. Because we really need to replace the dx. We can replace this. That's no problem. That's going to become u. Easy to do. But we have to somehow replace the dx term. So we have to think, okay, how can we handle that? So we have to get dx by itself. Now the problem is there's this e to the 2x. But note, e to the 2x is the same as u squared minus 1. So this is really u squared minus 1 times dx is u times du. Or dx is equal to u over u squared minus 1 du. And therefore, this becomes actually not such a bad substitution to make. So we can say the following. Say, look, this is the integral. This becomes u. And then the dx becomes u over u squared minus 1 du. The reason that this had any hope was the fact that when we took the derivative, it more or less looked the same, very similar. If we hadn't been able to solve for dx completely in terms of u in a nice way, it would kind of be a hopeless substitution. But as it turns out, it's not so hopeless here, so we're great. We're good to go. We need to do our bounds, so let's see what happens with our bounds. Okay, so what do we do? Well, suppose we plug in natural log of root 3. Okay, so what happens? The square root of 1 plus e2 natural log of root 3. Well, if you think about it, because of the properties of natural logs, you can bring the 2 inside. Square root of 3 squared would make that just log 3. E to the log 3 would be 3. So it's 1 plus 3, which makes that square root of 4, which makes it 2. So our lower bound is 2. How about our upper bound? Okay, we can probably do that one once we see this, right? We say, oh, it's like we have a root 99. So here it would be 99. Here would be 99, which means square root of 100, which would mean our upper bound would be 10. So that's why we had those really strange numbers at the start. Strange numbers at the start led to reasonable numbers at the end. And so that's oftentimes what goes on. Okay, well, now we say perfect. We really have a rational function. U squared over U squared minus 1. Great, great. And, well, first thing, we got to do some division, right? Because we have a U squared over U squared minus 1. So we're going to take U squared minus 1, divide into U squared. Well, it's not so hard. We just have one of them. And we have a U squared minus 1, subtract, which means that we'd have a remainder of 1. So I say, okay, so this integral here, it's the same as the integral from 2 to 10 of 1 plus our remainder, which is 1 over U squared minus 1. All right, well, now we do partial fractions. Okay, so this one will feel probably familiar, like we've done it before. So U squared minus 1 factors in a nice way. It's U minus 1, U plus 1. So it's going to be something over U minus 1 and something else over U plus 1. Okay, well, clear your denominators. 1 equals A times U plus 1 plus B times U minus 1. Clearing the denominators means you just multiply out. Okay, now we just pick nicely. U equals 1 gives us 1 equals A times 2, B times 0, 2A. So A is a half. U equals minus 1. Well, 1 equals 0 times A, and B times minus 2, minus 2B. So B is minus a half. Perfect. So, updating, we now have, look, this becomes the integral from 2 to 10 of 1, and then it's positive a half over U minus 1, so plus a half over U minus 1, then it's a minus a half over U plus 1. So minus a half over U plus 1 du. Okay, so those are easy things to integrate. So we have U plus 1/2 log U minus 1 minus a half log U plus 1. And evaluate that from 2 up to 10. All right, good. Well, we're rounding the corner. We're almost there. So we can now plug in. We get 10 plus 1/2, and then it'll be 10 minus 1, so that's 9, minus a half, and 10 plus 1, 11, subtract 2, then 2 minus 1 is 1, minus a half log 2 plus 1 is 3. Now, last thing we can do is we can just combine things together. Of course, the log 1 goes away. 10 minus 2 is 8. So we get 8. And all the logs have halves in them. So I can write a half log. And remember, logs can be combined together. So what do we see? There's a log 9 plus log 3 and a minus log 11. So you will multiply anything that's the added, so 9 times 3, and you would divide by the subtracted. So you'd end up with 9 times 3 is 27 over 11. And there we go. 27 11ths plus 8. Okay. Wow. What an answer. And actually, it wasn't so bad. Just a nice substitution. Do a little bit of long division, a little bit pulling apart, and things worked out. Cool. I feel like we can do more fun stuff now. More challenging problems. That's good. The more challenging that we can do, the better, right? Because that's the sign that we're growing and becoming better at calculus. Our next problem. Find the volume which results from rotating the region 0 less than or equal to x less than or equal to 1 and 0 less than or equal to y less than or equal to 2 over x plus 1 times x squared plus 1 around the line x equals 1. So they gave us a picture here. So, all right, interesting. Now, we see our function is not a very pleasant function to work with. This function is kind of hopeless to solve for x as a function of y. Forget it. Which means that when we think about our integration, we should be integrating with respect to x. And in particular, when we think about, okay, how do we break things up? Well, the way that we would break things up for finding volume is doing the vertical strips in this way. So we're splitting up our shape into this. We spin, and when we spin, what do we see emerging? The answer is shells. So this is going to be a shell method problem. All right, so if we're doing shell method, what do we need? Well, our volume is adding up, start to finish, 2 pi. There's a radius, a height, and a thickness. So this is how you find the volume of one of your shells, and then you add up all the shells together. So we should identify our pieces. It's not so hard to figure out A and B, 0 and 1. 2 pi, of course, is fine. The thickness, that's our dx. The thickness here is this little part. That's our thickness, that little tiny piece. The height comes from here. Okay, what's the radius? Well, the radius is how far your slice is from where you're rotating around. So if we think of our slice being located at x, it's the difference between x and 1, or between 1 and x. Of course, the question is which one is larger. So the rule of thumb is you take high minus low, right minus left, 1 minus x. So our radius is 1 minus x. Okay, so we have the following. This is the integral 0 to 1 of 2 pi. Well, let's just pull the 2 pi out. And then we take 1 minus x times that. So I can write that as 2 minus 2x over x plus 1, x squared plus 1 dx. Okay, well, great. Now, do we need to do long division? No. The power upstairs is 1, the power downstairs is 3. So we skip long division, not needed, and we go straight into partial fractions decomposition, pulling things apart. So what do we have? Well, we have 2 minus 2x. It's already factored as far as it'll go. X plus 1, x squared plus 1. We say, well, the denominator dictates how we break things up. There's going to be an x plus 1 term, and there's going to be an x squared plus 1 term. What goes over the x plus 1? Just some unknown, a. What goes over x squared plus 1? It's actually a little bit more. It's by plus c. Pay attention to y. The reason, bx. Why did I put y? Bx plus c. Pay attention to the reason. if you look, you'll see what you have down here is an irreducible quadratic. So when you have an irreducible quadratic, the numerator needs to have both the x term and the constant term. So in other words, it has to be a linear term. All right. Another way to always check your decomposition if it's right is that the number of things you're trying to figure out, in our case we're trying to figure out a, b, c, that's 3, it has to equal the degree of what's in your denominator. In our case we have a degree 3. So the good news is 3 equals 3, so we're on the right track. Clear off our denominators. Okay, so that leads us to the following. 2 minus 2x is equal to a times x squared plus 1 plus bx plus c times x plus 1. And now we start picking nice values. Okay, well, that's not the only way to do things, but again, I like to do things this way, and I'm very biased. Whatever you're comfortable with, do it your way. As long as you get the right answer, that's great. So some nice values. I like plus 1. Make the x plus 1 0, so that would mean negative 1, right? And if we chose negative 1, 2 plus 2. So that would be 4, right? 2 minus 2 times minus 1, 4. This last term, whoosh, away it goes. And here we'd have minus 1 squared, which is 1, plus 1 is 2, is 2a, which means a is 2. Perfect. We've already got a. And we've just barely begun. Well, what's another good value? Well, 0 is not bad, right? Because 0 knocks a term out. So 0, it's oftentimes a good go-to value if you don't have another nice go-to value. So at x equals 0, well, we'd have 2, because that's 2 minus 0, equals a. But wait a second, we know what a is. A is 2. Okay, so that equals 2. And then we're going to have 0 plus c, which is c, times 0 plus 1, which is 1. So 2 equals 2 plus c. Okay, great. That tells us c is 0. Okay, gone. Whoosh. All right, well, one more value. Well, let's go with 1. Not because it's going to knock anything out, but it's an easy number to work with, and we've kind of exhausted the ones that knock things out. 2 minus 2 is 0, and that's at least something. We're going to get a times 2. Well, we know a times 2 is 4, because we know what a is. So that's 4. Then we're going to get b times 1 plus c. Well, wait a second. We already know c is 0, so that's going to be b, and then 1 plus 1 is 2. So 4 plus 2b equals 0. Okay, subtract 4, divide 2. That tells us that b is negative 2. All right, so that's negative 2. Wonderful. These are nice numbers to be working with here. Okay, so we're ready to go back and update. So we have our 2 pi still out in front, integral 0 to 1. And this integral becomes 2 over x plus 1, then minus 2x over x squared plus 1 dx. All right, well, now we can integrate all our pieces. They're all on the board, ready for us to go. So let's see, what do we get? We get 2 pi, and we're going to get log, there's a 2 in front, 2 log of x plus 1. Now here, 2x over x squared plus 1. Function downstairs, derivative upstairs, that says we're going to get log. So in particular, it's log of x squared plus 1. If you're not comfortable with that step, by the way, one thing you can always do is do a substitution. if you let u equal x squared plus 1, du is 2x dx, and away you go, off to the races, so to speak. All right, well, good news. When you plug in 0, you get a log of 1 there, which is 0, and a log of 1 there, which is 0. Nice. So we just need to plug in 1. Okay, so plugging in 1, we're going to get 2 pi, and then here we're going to get 2 times log of 1 plus 1, which is log 2, subtract log of 1 plus 1, well, which is log 2. Well, okay, 2 log 2 subtract log 2. That's actually pretty easy to simplify. It's log 2. So we end up with a 2 pi log 2. And that's, as answers go, pretty clean answer. Pretty clean answer. We would have been very happy with an answer like that. I think we would be. Well, we are, so good. Well, we should do some more. Let's do some more problems. All right, our next problem. Find the integral 4 to 9 of dx divided by x to the 3/2 minus x to the 1/2. Now, is this a partial fractions problem? Not yet. Okay, remember, be careful. Partial fractions only applies if it's polynomial over polynomial. And x to the 3/2 and x to the 1/2, they're not polynomial. The powers need to be whole numbers. So this is a unwhole problem, right? Because the powers aren't whole values. So we can't do partial fractions yet. It's possible, very likely, because that's what we're talking about, that partial fractions eventually can be used, but we have to wait. We don't know. Not yet, but maybe, if we live a good life, things will happen. Now, we can't do partial fractions. What can we do? Well, what we can do is we can start to look about how are ways to rewrite. A lot of times integration comes down to saying, maybe if I rewrite it in the good way, something will pop out. So one of the things is I say, well, look, downstairs, they both have common things. They both are powers of x. Let's pull out the common term. And I think that's a reasonable thing to do. So this would be the integral 4 to 9 of dx. And what they have in common? Well, x to the 1/2 power. So we can write it as, okay, let's be careful here. If I have x to 3/2 and I'm pulling out x to the 1/2, what's left? It's x to the 1. So it'd be x minus 1, x to the 1/2. Now, the next thing, now that I see this, I would start thinking, one of my initial reactions whenever I see a problem is there a nice substitution sitting there? And I kind of see one. And I think, hopefully, I hope we agree that there's a nice substitution sitting here. This x to the 1/2 is very tempting to think of in terms of substitution. What do I mean? Well, if I think about it, whenever I'm looking for a substitution to make, one way to look for a substitution is to say, do I see a function which is a derivative? In other words, do I look at a piece and say, hey, I know you. You are a derivative of something. And x to the 1/2, are really more precisely x to the negative 1/2 because it's downstairs, is such a thing. So we can think of this as 4 to 9, and I'm going to write it as 1 over x minus 1. I'm just going to sort of separate these. I'm not trying to set this up as partial fractions. That's not my goal. And looking at this, say, well, maybe this is a du? Maybe. What would u need to be? So in other words, what would produce a derivative of x to the minus a half? What does that? X to the 1/2. X to the 1/2 does that. So we say, if you let u equal x to the 1/2, then du would be 1/2 x to the minus 1/2 dx. Well, okay, there's a 1/2 there. All right. Constants are okay. We can work with those. So that moves across. 2 du is x to the minus 1/2 dx. Like, okay. Well, what happens to everything else? Well, now we see, okay, the bounds are nice because it's the square root of 4 is 2, square root of 9 is 3. That maybe was another clue we should have been thinking about square roots. When you see suspicious numbers like, wait a second, both these numbers involved in my bounds are squares, why would they do that? Well, because they would probably be saying, they're setting ourselves up where it's nice to have a square number. Well, that's a clue that square roots would be involved in our substitution. You see, you start to be like a little, like, there's a puzzle here. Let's see if we can't unravel this puzzle and figure it out. All right, well, the 1 over x to the half dx, look, we know how to handle that. That would become a 2 du. Now, the last thing for us to figure out is this x minus 1. Well, that's not so bad. You see, we could have said here, u squared equals x. That would have made it not so bad. We could have said, look, dx is 2u du. But, all right, what do we get? X becomes u squared, so it's u squared minus 1. And now we're like, ooh, that's why we're doing this. It is now a rational function. You see, before, at the very beginning, nope, not rational function. It's not polynomial. But now, it's polynomial. And so we're like, yes, good. So we're in great shape now. We're ready. So do some work on the side here. We're going to say, look, 2 over u squared minus 1. Well, that's u minus 1, u plus 1. So that's something over u minus 1 plus something over u plus 1. Clear your denominators. So we'll get 2 is a times u plus 1 plus b times u minus 1. All right. And, of course, clear your denominators just means multiply by the denominator there. And make good choices. Make good choices. For example, learning calculus. Great choice. All right. Of course, there's other good choices you can make. In our case, u equals 1 is a great choice because that knocks that term out. We'll get 2 equals 2a. That's a beautiful choice. So a equals 1. How about negative 1? Another good choice, right? Because negative 1 will knock that term out. So we get 2 equals, that's gone, b times minus 2. So minus 2b. So b is negative 1. All right, cool. So this is 1, and this is minus 1. Now, we say, great, we're ready to jump back to our problem. We've done our partial fractions, which lets us pull it apart. So this becomes the integral from 2 to 3 of 1 over u minus 1 minus 1 over u plus 1 du. All right, that's natural log of u minus 1 minus natural log u plus 1. And we're going to evaluate from 2 to 3. So the last thing for us to do is to evaluate. And notice here, we're not going, now we got to go back to x. No, that's not what we need to do. When we're doing a different integral, as long as we update our bounds, we're always like, we're moving forward. We're never looking back because our bounds have been updated and we don't have to go back. So we have natural log of 2 subtract natural log of 4. And from that, we're going to subtract natural log of 1 minus natural log of 3. All right. So what happens? Well, natural log of 1, 0. That goes away. Minus minus makes a plus. And remember, when we add, we multiply. When we subtract, we divide. So truly, natural log of 2 times 3 over 4. But you can clean that up. So we get the natural log of 3 halves. That's it. We're done. Wow. Cool. Fun problem. Good problem. All right. Well, let's try another one, right? We should try another problem. Okay. So, find the integral dx over e to the 2x minus 1. And let's try a couple of different ways. Actually, I'm going to try to do this 2 different ways just to show you that there are different approaches to problems. And you don't always have to do things in one way. You might have options, and be open to more options. Being open to options is wonderful. It's nice. Okay, well, in both of them, when I say both of them, or when I talk about in both approaches, we really want to say, look, we can't do much in its current form. Definitely we can't do partial fractions yet, because we're not ready for partial fractions. We need to somehow rewrite it in a partial fraction-friendly way. So we're going to do some substitutions first to help us to rewrite it. So one of the things to say is, e to the 2x, whenever you see something like e to something x, you should always say, maybe they really are hiding something. Maybe they really mean e to the x squared. So the first substitution we'll make is, let's try u equals e to the x. All right. If we did that, we'd have du as e to the x dx. Well, of course, e to the x is u, which says, all right, that's the same as saying dx is 1 over u du. So we end up with the integral becomes, well, we have a 1 over u squared minus 1. And then the dx is another 1 over u du. So this u here is part of the dx. Now we are into a rational function. Okay, good. So we can do partial fractions. And we're going to do the partial fractions a little bit quicker, because we are doing this 2 ways, right? So we don't want to spend too much time on any one single approach. So we say, okay, look, this is really 1 over u minus 1, u plus 1, u, and that's something over u minus 1 plus something over u plus 1 plus something over u. Clear out your denominators. 1 equals a times u plus 1 times u plus b times u minus 1 times u plus c times u minus 1 times u plus 1. And once we've done that, we can quickly come to our conclusion about what a, b, c need to be, right? Because we just choose. For instance, choosing 0. If we let u equal 0, we're going to get 1 equals minus c. So that tells us what c needs to be. C needs to be -1. All right, choose another good value. How about 1? Okay, that knocks out the last 2 terms. 1 equals 2a. Okay, perfectly fine. That tells us here that a is 1/2. All right, how about -1, right? Because that would knock out some terms. Well, we're going to get 0, 0 here. -1 times -1 is -2 times -1 is 2. So we get 1 equals 2b. Well, so that says that b is also 1/2. Okay, great. And so we're saying hey, this is lovely. Lovely stuff. So our integral now updates to the following. We have the integral 1/2 times 1 over u minus 1 plus 1/2, 1 over u plus 1, and minus 1 over u du. So integrating, that's 1/2 log u minus 1 plus 1/2 log u plus 1 minus log u plus c. And go back to what u is. U is e to the x. So that becomes 1/2 log e to the x minus 1 plus 1/2 log e to the x plus 1. And log of u, log of e to the x, is x. And we're done. Okay, now remember we're doing this in two ways, and so we left ourselves plenty of space because we still need to do our second approach. Our second approach says, okay, go aggressive. What do we mean by go aggressive? Instead of saying, oh, u is e to the x, oh, make u equal just the whole denominator. Okay, so u equals e to the 2x minus 1. All right, well, that's fine. We're perfectly allowed to do that. Then what do we have about du? Well, du is 2 e to the 2x dx. But now we say, wait, hold on a second. We know what e to the 2x is. E to the 2x is u plus 1. So this becomes 2 times u plus 1 dx. Or we can say, aha, dx is really 1 over 2 times u plus 1 du. Okay, so what does our integral become? Well, so our integral becomes the following. It's the integral of, there's a u there, so I have a u, and then from the dx term, there will also be a 2 and a u plus 1. Okay, so that's where we're at. That's where it becomes. Great. Well, let's do partial fractions, right? Because it's a polynomial over polynomial, just right for partial fractions. Just right. Okay, so we have 1 over 2u, u plus 1 is something over u plus something over u plus 1. Notice it's actually a different problem, right? Because here there were 3 terms, and here there's only 2. So it's definitely not the same thing we just did. So that's good. Of course, that means we still have to figure out what it becomes. Clear denominators. And what do we get? Well, we get the following. We'll get 1 is equal to a, whoops, not 1. Yeah, it is 1. 1 is equal to, when I multiply through, 2 times a times u plus 1 plus 2 times b times u. Right? Yeah, that's what we'll have. Okay, good. Now, choose wisely. Well, we see 0 is a great choice. So u equals 0. We come to the conclusion that 1 equals 2a. Okay, so that really says a equals a half. All right, great. So this part here, this is 1/2. Well, what's another good choice? Well, another good choice would be -1. So if u is -1, well, we get 1 equals, here, that goes away, and then we have, what, minus 2b. All right. So what does that tell us? Well, that tells us b is -1/2. Okay, well, great. So we've got a and we've got b. 1/2 and minus 1/2. So now we update. So what does our integral become? This becomes the integral of 1/2 times 1 over u minus 1/2 1 over u plus 1. And of course, du. And now when we integrate, that's 1/2 log of u minus 1/2 log of u plus 1. Now we have our plus c. All right, good. Well, we got to put back what things are. What is u? U is e to the 2x minus 1. So we get 1/2 log of e to the 2x minus 1. And here, well, what do we have? We got to really unravel this one for a second here. So let's start. U plus 1 is e to the 2x. So it says it right there. U plus 1 is e to the 2x. All right? So log of u plus 1 is 2x. Right? Because log of u plus 1 is log of e to 2x, which is 2x, times 1/2. Well, I get rid of the 2, so it becomes minus x. And then, of course, plus c. And we're done. See? And we did it 2 different ways, and we got... Oh, wait. Are they the same? They should be the same, right? Well, yeah, they should be the same if we did it in 2 different ways, because the answer doesn't depend on the method. Now, but the key here is that the expression of the answer might depend on the method. Can we make these look the same? Well, we can. And here's the thing. Notice these 2 log terms are being added. We could have combined them together, and if you did, that would be 1/2 log of e to the x minus 1, e to the x plus 1. And now you see a minus b, a plus b, which becomes 1/2 log a squared minus b squared. So these 2 terms equals that term. Same answer. So it goes to show you that you can do things in different ways. All right, well, I think we have time for one more problem. So let's do one last problem. Just a nice cool down. Nice one to finish up with. Find the integral of 4 secant squared theta over 5 minus secant squared theta d theta. All right, a nice trig integral to finish our partial fractions work. But when we look at this, we say, oh, maybe there is something going on, because downstairs kind of feels like a polynomial. And so, okay, but what are some clues? So when we look at problems, we should always say, are there clues on what I need to do? And if we can start to pick up on these clues, then we can start to say, oh, there's some fun stuff going on here. And for me, there's like a big clue. And do you see it? I think we both are looking at the same thing. I see this secant squared on the top. That's a big clue to me. Because what that really is saying is, ooh, I can think of the integral here in the following way. This integral we can be written as 4 over 5 minus secant squared theta times secant squared theta d theta. How does that help us? Well, the reason it helps us is secant squared isn't just any run-of-the-mill function. It's one of the functions that shows up as a derivative of a nice function. So we could say, aha, this would be du if we were to choose u as tangent theta, because the derivative of tangent is secant squared. So it says, hey, there's a nice substitution that is potentially available because we see a derivative showing up. But the only way we can make it work is we have to come to this first piece and say, can we rewrite this And in particular, when we say rewrite, can we rewrite it so it's all in terms of tangent? Currently, there's no tangents at all, so that's not the most promising thing, but there is a secant squared, and there's a nice relationship between secant squared and tangent. In particular, we can say the following. This is the same as secant squared is tangent squared plus 1. And now we're like perfect. We're ready for our substitution. So we make our substitution. U equals tangent. du is secant squared theta d theta. And what do we have? Well, we have 4 over 5 minus 1 is 4. Tangent squared, u squared, secant squared theta d theta is du. And that, we say, great. In fact, that's what? That's really 2 minus u, 2 plus u. All right, well, fantastic. Now we just need to go do a little bit of work on the side with some partial fractions. It's our cool down, so shouldn't be too bad. 4 over 2 minus u, 2 plus u. Well, that's something over 2 minus u plus something over 2 plus u. Clear off our denominators. 4 is a times 2 plus u plus b times 2 minus u. All right. Choose some nice values. We choose u equals 2. 4 is 4a. A is 1. If we choose u equals minus 2, 4 is 4b. Wow. Wow, they love us. Whoever picked these numbers, they were like, hey, let's care about people. Let's let them have fun. So these are both 1s. So now we can say, all right, going back to our problem, this is the same as our integral of 1 over 2 minus u plus 1 over 2 plus u du. Okay, well, those are both easy things to integrate. So that would be log of 2 minus u. Would it? Be careful. Okay, so this is a place where I know I've made mistakes in the past on this type of step. So I'm like, no. All right, let's check ourselves, because after all, it's important that we check ourselves before we wreck ourselves. Is that correct? And why not? It is not correct. Okay, good. And the reason is that there's a minus there. So you have to account for that minus. So it's really minus log 2 minus u. And the next one, it is a plus log 2 plus u, because it's just that. That's perfectly fine. Okay, so we can actually combine these together into one single log. So we can write it as log. The 2 plus u is being added. The 2 minus u is being subtracted. So that means the 2 plus u goes on the top. The 2 minus u goes on the bottom. Now, we got to go back in terms of our original variable. So we got to go back to secant, because that's where we began. So this becomes log of u is tangent. So it's 2 plus tangent theta divided by 2 minus tangent theta plus c. And we're done. Great. That was a very nice, pleasant cool down. Very nice, pleasant cool down. Well, I hope you enjoyed doing partial fractions. I know we haven't done really crazy problems, but I don't think that doing crazy problems are how you get better. It should be practice on the basics. Drill the basics. And then once you get more complicated, you say, look, it's really just the basics with a little bit of extra keeping track of things. And the ideas are there. Figure out your decomposition. That's the hard part. Once you've got your decomposition, great. Now, clear your denominators and figure out how to solve for your constants. I like to choose good numbers. If you like to expand out and compare coefficients, that's great as well. And The moral is pull it apart, integrate the integration part. It's actually going to be not bad. The whole point of partial fractions is not doing hard integrals. It's rewriting crazy expressions in a simpler way. And that's actually a big idea in calculus. All right, well, I suppose the moral is simplify. Simplify. Keep things simple. Whew. Good lesson for calculus. Good lesson for life. Thanks for coming. Appreciate you spending the time. Hope to see you again. Bye.